Hello everyone, thanks for watching this video. I am Wanhua Li, a third-year PhD student from Tsinghua University. Today I am going to talk about our work GKR, which is a graph-based kinship reasoning network. Some research in biology finds that human facial appearance contains important kin-related information. Inspired by this finding, many methods have been proposed for kinship recognition from facial images. The goal of kinship verification is to determine whether a kin relation exists for a given pair of facial images. Although a variety of efforts have been devoted to kinship verification, it is still far from ready to be deployed for any real-world uses. There are several challenges preventing the development of kinship recognition. First, as other face-related tasks, facial kinship verification is also confronted with a large variation of the pose, scale, and illumination, which makes learning discriminative features quite challenging. Second, unlike face verification, which investigates the relations between different images of an entity, kinship verification has to discover the hidden similarity inherited by genetic relations between different identities, which naturally leads to a much larger appearance gap of intra-class samples, especially when there are significant gender differences and age gaps in kinship verification. Many methods have been proposed to address these challenges over the past few years. Most of them pay attention to learning discriminative features for each facial image of a paired sample. However, these approaches usually apply a similarity metric or MLP to the extracted features to obtain the probability of kinship between two facial images, which couldn't fully exploit the genetic relations of two features. In this paper, we focus on the aspect of how to compare and fuse the two extracted features of a paired sample to reason about the genetic relations. We hypothesize that when people reason about the kinship relations, they usually first compare the genetically related attributes of two individuals, such as cheekbone shape, eye color, and nose size, and then make comprehensive judgments based on these comparison results. For two given features of a paired sample, we consider that each dimension of the feature encodes one kind of kin-related information. Therefore, we explicitly model the reasoning process of humans by comparing the features for each dimension and then fusing them. More specifically, we build a star graph named Kinship Relational Graph for two features to perform relational reasoning, where each surrounding node models one dimension of features and the central node is utilized as a bridge of communication. To formalize the problem, we first use function g to denote the feature extractor. Handcrafted methods usually design shallow features by hand to implement the extractor g, whereas deep learning-based methods usually learn a deep neural network as the extractor g. Metric learning-based methods usually first use handcrafted features or deep features as the initial sample features, and then learn a distance metric. In the end, we obtain the projected features using the learned distance metric. Having obtained the features, we still need to learn a mapping function f to map the features to a probability of kin relation. One choice is to simply concatenate two features and send them to a MLP. Another commonly used way is to calculate the cosine similarity of two features. Both methods can't fully exploit the relations of two features. In this paper, we aim to design a new f to effectively perform relational reasoning on the two extracted features. More specifically, we build a kinship relational graph and performs relational reasoning on this graph. In recent years, deep CNNs have achieved great success in many computer vision tasks. Therefore, we utilize a deep CNN as the feature extractor G. Having obtained the deeply learned sample features, we consider how to perform relational reasoning on them. To achieve this, we first observe how humans reason about kin relations. As the genetic traits are usually exhibited by facial characteristics, humans reason about the kin relations by comparing the genetically related attributes to discover the hidden similarity. After comparing a variety of informative facial attributes of two persons, humans make the final decision by combining and analyzing all the information. We explicitly model the above reasoning process by constructing a kinship relational graph and performing relational reasoning on this graph. We consider that each dimension of the extracted features encodes one kind of genetic information, and we can reason about the kin relations by comparing and fusing all the genetic information. Since we use the same CNN to extract features for two images, the values of two features in the same dimension represent the comparison of one kind of kinship-related information encoded in that dimension. We use one node in the Kinship relational graph to denote the comparison of one feature dimension, then we have D nodes which describe the comparisons in all dimensions. To fuse these comparisons, we need to define the interactions of these D nodes. We create a super node that is connected to all other nodes. The super node is also the central node of the star-structured Kinship relational graph, which plays an important role in the interaction and information communication of D surrounding nodes. In this way, we build the Kinship relational graph. Having built the Kinship relational graph, we perform relational reasoning on this graph by employing a recursive message passing scheme. We first generate the message of each node which is going to be sent out in the following message passing process. We apply the same operation for the central node with the same parameter. With these messages, we propagate and aggregate them according to the graph structure. Then we update the node features with the aggregated messages. For the surrounding nodes, since the central node is the only neighbor node, the aggregation is implemented by concatenating the message of the central node and its own message. Then we use the aggregated messages to update the node feature. For the central node, we first aggregate all the incoming messages. Then the feature of the central node is updated with the aggregated message. We repeat the above process for k times and have the final node feature vectors. To make the final decision, we first combine all these features and send them to an MLP, which outputs a scalar value. We employ the binary cross-entropy loss as the objective function and train the proposed GKR end-to-end. We conducted extensive experiments on two widely used kinship verification datasets, KFW-I and KFW-II, to illustrate the effectiveness of the proposed GKR. We first compare our GKR with several state-of-the-art methods including metric learning-based methods and deep learning-based methods. We observe that our method achieves an average verification accuracy of 79.2% on KFW-I and that of 90.6% on KFW-II, which outperforms state-of-the-art methods. Compared with WGEML, our method improves the mean accuracy by 0.5% and 7.8% on KFW-I and KFW-II, respectively, which shows the superior relational reasoning ability of the proposed GKR. Zhang and others propose the CNN basic and CNN point, which directly learn deep neural networks for kinship verification to exploit the power of deep learning. Our method, which is also a deep learning-based method, outperforms the CNN point by 1.7% and 2.2% on KFW-I and KFW-II, respectively. Note that the CNN point contains 10 CNN backbones whereas our approach only employs one CNN backbone, which further illustrates the effectiveness of the proposed GKR. To investigate the influence of individual design choices and validate the effectiveness of the proposed GKR, we further conducted ablation experiments. The initialization of the central node is an important design choice given that the central node is the bridge of the kinship relational graph. One strategy is to aggregate the initial values of all other nodes by mean or max pooling. Another way is to initialize the central node with constant values, such as 0, 0.5, and 1. The results show that the initialization with constant value 0.5 gives the best performance, which is employed in the following experiments. We also have two different pooling operations for function aggregate, max pooling and mean pooling. We observe that the max pooling achieves better results, perhaps it can better select more important information while the mean pooling treats all messages equally. To validate the effectiveness of our proposed GKR, we compare it with other widely used design choices for mapping function f, one as MLP and the other as cosine similarity. We see that our method outperforms the MLP and cosine similarity by a large margin on both databases, which demonstrates that our method can better exploit the relations of two extracted features and perform relational reasoning with the kinship relational graph. Thanks for watching my presentation. If you have any question, please feel free to ask or contact me via email.